final the section 4 on open source implementations, and here it talks about mostly the concept of within operating systems. Okay, so first of all, we talk about the open versus closed, and open source package and Linux system, the software architecture, and then kernel, drivers, and daemons. So what is open? Okay, or what to open is probably the first question. Is it an open interface or open implementation? So when we are talking about open, we need to be aware: are we opening the interface or opening the implementation? So the internet has an open interface, meaning that the standard, the protocol is open standards. However, on the internet, there are a lot of devices. Their implementations are open or closed. And Linux is the open implementation, and some other implementation are closed. So one example of closed, two examples of closed is IBM SNA. The IBM SNA is another protocol stack compared to TCP/IP, and it's closed. So and it's proprietary. So it's a closed interface. IBM does not want any devices following the SNA architecture or SNA protocol stacks. So what it does is that it tries to grab and constrain the customers. So one day you are IBM customer in networking, then you are IBM customer forever, because no other company can produce networking devices following the SNA protocol stacks. So it's closed interface. And even though you can, it's not, the protocol are not open documents. The protocol documents are not open. And even though you could do reverse engineering to understand the SNA protocol stack, but if you do products that are compatible, that can talk in SNA, then it's possible you could be sued by IBM. So you cannot do that. So it's closed interface, closed protocol. However, and Microsoft is closed in what? On implementation. Microsoft have open interface. Microsoft operating system have open interface. It opened up the development kit, which is called MSDN, Microsoft Development Network, that has all the development kits available. So you know the system code, the functions, and the command. So these are open. Why Microsoft opened this up? Because in a hope that more application developer would write application program for Microsoft, and they run on Microsoft. So they need to open up this system code, library function code to the developer, application developers, so that more application developers will write program for Microsoft OS platforms. Okay, so however, Microsoft although Microsoft opened up the interface, but it closed the implementation. It does not open up its implementation for the commercial interest. Okay. Then we look at why do we need to open interface, or why do we need to open implementation. The open interface would introduce better interoperability, meaning that product produced by different vendors will be able to interoperate, right? As long as you follow TCP/IP protocol stack, you are likely to interoperate with the other products, with the other vendors' products. So open interface will improve the interoperability between vendors. How about open implementation? What's the point to open implementation? Some advantages are worldwide contributors. The source code could be contributed by worldwide by multiple people, and also the bug could be fixed by multiple people. So I write a code and with some bugs, but I don't have time to debug. Somebody else might be able to debug for me. So I could have fast update and patches on the source code to fix the bug. So in general, there will be a better code quality. Well, in general, not necessarily true, but in general. Perhaps in Microsoft, each piece of the code could probably is only watched by 1 or 2 persons, right? Only a few people, a few engineers will watch the code, that particular piece of code. However, on the internet, if there are some buggy problems, then that piece of code might be watched by multiple people, and they probably could fix the bug quickly. So in general, the code quality is better. So that's the point for open implementation. And we'd like to look at 2 examples. One is the 2 example router and server to see their software architecture on Linux system. Okay. And in explaining this, you will need some concept of operating systems. See, this is a router with at least 2 interface cards. So I have 2 interface cards, and then and I have my kernel space here, the Linux kernel. And then on top user space, there are some programs, some daemon programs on top. And what happens is that if a package come in, if there's a packet come in, what happens is that if this is a data packet, then it will go through, it will generate interrupt. The interface card will generate hardware interrupt, so that the CPU control on the motherboard, the CPU control is passed through the device driver, to pass through the driver, and then and so the packet, so the driver will read the interface card. There's a register for the driver to read, to know the status. Okay, once the driver read the status, it knows that okay, there's a packet coming in, and I need to tell the DMA where to move the packet in. I need to tell the DMA where to move the packet in. So I issue command to tell the DMA. Okay, and then that's done. And then the DMA starts to work to move the packet from the interface card to the memory on the main memory. So DMA will start to work to copy the packet from this to this, and then to the kernel space. And then once done, the interface card generate another interrupt. Okay, and then the control is passed through the driver again. The CPU control is passed through the driver, and then read the status. Okay, it says okay, the packet is there. It's packet moving from the interface card to the memory is done, and it's there. So the driver will start to move the packet, to process the packet here, and then pass it to the protocol driver, which is the TCP/IP, the IP layer, push to the IP layer. And at the IP layer, it would look up, the IP layer will look up the routing table in order to decide where to move the packet to, where to forward the packet to. So it would do the routing table lookup, and then decided to pass through this interface. Then it will pass through the driver, and then the driver issue command to the register on the interface card, saying, okay, I have packet on this address, and you can go ahead to move the packet and then transmit it. Then the driver is done, and then the DMA will start to move the packet, and then the car will start to try to transmit the packet. Once successfully transmit the packet, it will generate another hardware interrupt. Okay, and then the controls of the CPU is passed through the driver again, and the driver will read the register, okay, to know, okay, the packet transmission is successful and it's done. So you will see that in handling this, it involve hardware interrupt. It involves the driver, and then the driver pass through the IP layer. The IP layer needs to look up the table, and then push through another interface card. Okay. However, if this packet is a control packet, then it might be a routing message exchange with neighbors, okay, or broadcast from the other router. Then the control message will go up again, the similar process. There'll be hardware interrupt, and the driver will need to issue command to the DMA. That DMA stands for dynamic memory access. Okay, and then it will go the way up to the daemon process because it's a protocol message, routing protocol message. And then the routing protocol message will trigger the shortest path computation here. It will trigger the shortest path computation, and then once it finishes the computation, it will update the routing table in the kernel. So these are if it's a routing message, then it will be passed through the routing daemon. Then one question you might ask is, why do we put the routing table in the kernel, but put the calculation in the daemon? Why don't we put the calculation in the kernel together with the routing table, or put the routing table into the daemon? Why do we separate them? So the table is here, but who calculated this table? Who up this in the daemon? Why not put them together in the kernel or in the daemon? Okay, if you put this calculation, the routing calculation, in the kernel, it would complicate the kernel, and if there's an error or some problem, then the kernel might be crushed. If kernel crushed, then the whole machine is down, right? So the principle is that you don't want to put too complicated code into the kernel. You want to put stable, very stable and simple code in the kernel. Okay. So that's one reason. You don't want to put it here. You want to leave it here. Then why don't you put the routing table here? That if you put the routing table here, then I cannot do the forwarding decision in the kernel, right? So all the data plan packet will need to go up to the daemon and do the table lookup there. Then all the packet need to cross the boundary of kernel space and user space. And you know, when you cross the boundary, when the data needs to cross the boundary of the kernel space and user space, you involve two things. One is the memory copy. You need to copy from the user space to the kernel space, or vice versa. And the other thing will be software interrupt. In the user space, if you need kernel to do something for you, say you want to read and write through the kernel, then it would generate software interrupt, which is system call. System call will generate software interrupt. And so you would have software interrupt by system call to handle, and also memory copies between user space and kernel space. So you want to avoid too much traffic or too much data crossing the boundary of kernel and user space. So you want to keep most of the data in the kernel. So if we say that say 99% of the packet are data packet, right? Only 1% are control packet. So most of the packet will go through this, and they will be processed within the kernel. And of course, there are memory copy between the interface card and the main memory, and then main memory to the interface card. But just that, no more. You don't want to do the memory copy here for 99% of the packets. Okay, so only 1% of packet will need to cross the boundary of user and kernel space. So that explains why a router the component of the router are arranged in this manner. Okay, how about a server? A server would have, usually a server does not have two interface cards. Mostly just one interface card will be enough. And then the structure is simple. However, most of the packets will go up to the user space. Because of what? Because of this daemon process cannot be put into the kernel. It's too complicated. The Apache server, the mail server, these are too complicated, and they can only be kept in the daemon. So all the data packet needs to cross the boundary. It's inevitable. And there's some control packet here, but it's only between, say, ICMP. If you got ICMP, then the ICMP is implemented here in the kernel, so you need to handle some error reporting by ICMP. But mostly just through the daemon. And these are the Linux operating system structure. You got hardware and some hardware dependent part, and then a hardware independent part, and then applications. So these are the kernel space. And you can see that networking is only 1/5 of the entire OS. How about the other 4/5? That'll be process management, memory management, file system, and device control. So networking is only 1/5 of the entire OS. And you will see that we implement the physical layer and link layer in the hardware, mostly. And then the driver, and then the IP layer here, the driver, and then IP layer, TCP IP here, and then application in the user space. Okay, I think I will stop here, and I still have some to finish for chapter 1, so probably I need to take 40 minutes next week to finish. But still, please start to work on your homework. Number 1. Yes. Any question? Most people say routing table, but less people say forwarding table. But they are the same. Where it give you a destination network. The entry is per destination network. It would have an entry for the next hop. I mean, for each destination network, you would have a next hop interface to forward the packet through. And it's irrelevant. It's irrelevant to how many flows passing through this router. You might, well, say in an intro-domain router, because I'm handling, say, 256 subnet, I probably have 256 entries in my routing table in the intro-domain router, at, say, for example, within NCTU. However, in this router might have 10,000 flows passing through, but I don't have table entry to keep track of them. I have a routing table with 256 entries for each of the, each entry is for each destination network within this domain, but I don't have entry to keep track of these 10,000 flows passing through me right now. I don't. So I'm still stateless. And if I become MPLS switch, then I would have state I would have entry in the MPLS table for some of the flows. For some of the flows, I would need to keep track of them because I do switching for some of them. Then I become stateful. Yeah. But usually the router does not do that unless you are MPLS switch. But most of the IP routers are stateless, and they don't maintain that state.